thought just as a little digression, we could go back to an example we talked about last class. This data here about machine, heads on the machine, and some repeated measurements on those different things. Anyway, this is a nested model. And anyway, it gave us this information about the expected mean squares. And so if we look at this, we can see the testing is kind of obvious. If we want to test about factor H, here's the denominator we would use, the error. If we want to test about factor M for machine, the denominator would be the second one here. And so with this in front of our eye, we know how to run the f-test really neatly. But anyway, since this was rather small, I thought this might be a good little example to use to check out the algorithm for figuring out the expected mean square column. So if you could go back and find your page, which I gave you weeks ago, this one about expected mean square rules. And I'll use this as the guide for what we're doing here on this problem. So anyway, it says the first thing to do is to write down the terms in the model in the column on the left, and then fill in this information along the top about sizes of things. So if I come to this example and try to do that, let's see here. I would list down what they have here. M, I, H, J nested in I, and then the error E. K. Well, since this handout does it, I'll do it here as well. K nested in I and J, although that fancy notation isn't really needed so much. So anyway, we have that for our start. So we put this here, we put this here, and we say, well, the subscripts are I, J, and K. And as far as whether these factors are fixed or random, in this particular example, the machines were fixed and the heads were random. So I would put an F there, fixed, an R there for random, and an R there for random, and get that much filled out. Now I have to put in the numbers of things. On the machines, there's 1, 2, 3, 4, 5, so I goes 1 to 5. J, the head, goes 1 through 4. So I'll put a 4 there. And then the replication is again 4. So I'll put that there. So there's an easy start to the process of figuring out the expected mean squares. Now the method says, once we get that done, it says for each row, copy the number of observations under each subscript, provided the subscript does not appear in the row heading. So if I try to follow those directions, where am I at here? If I try to follow those directions, I would say copy the number of, how does it express again? The number of observations under each subscript, providing the subscript does not appear in the row heading. So if I try to copy down to 5, I can't put it there because the I is in that row. I can't put it there because the I is in that row. And I can't put it there because the I is in that row. So the 5 doesn't do anything for me in that step. So I move to the next column of 4, and I say, well, that's connected with J, and so I'm going to put a 4 there because that row is subscript I. Now I don't put anything in the next entry of that column because that entry has a J in it. So I skip that one. And so that's all I've got. So then I finally come to the third column, the K column, and I say, well, I've got 4 of those. I'll put a 4 here. That row doesn't have any K in it, so that's okay. I come to the second row, that doesn't have any K in it, so I'll put another 4 there, and then I don't put anything here for the last row because there's a K there. So completing that step, I've got that much done. Now we come to step 4, which says, for any parenthetical subscripts in the model, place a 1 under subscripts given in parentheses. For any parenthetical subscripts in the model, place a 1 under subscripts given in parentheses. So if I try to follow those directions, I should put a 1 apparently here. And then by the same token there and there. Okay, so for any parenthetical subscripts in the model, place a 1 under subscripts given in parentheses. So I guess I do that. Now we come to step 5. Fill each remaining cell with a 0 or 1, 0 for fixed, 1 for random. So then I would say, let's put a 0 in there, because that's a fixed factor, and the second factor under J is random, so I'll put a 1 there. And then by the same token, the third column here is random, so I'm going to put a 1 there. So with all this pickiness, I've got this much figured out in the table. Now we have to try to use this. So it says, come to step 6. Cover the entries in the column that contain non-parenthetical subscript letters in this term in the model. So for example, let's cover this column here on I. Multiply the remaining numbers in each row. Each of these products is the coefficient of something. So let's see, let's multiply these numbers. I get 4 times 4 is 16, 1 times 4 is 4, 1 times 1 is 1. So if I just jot those down for remembrance, I get 16, 4, and 1 for those products. So now it says those numbers are supposed to be the coefficients in the expected mean square. And if you look over here at the result for M, I have a 16M, I have a 4H, and I have a 1 plain sigma squared. So those 3 coefficients are coming from these 3 products here. Right. So now I cover the second column there, and I look at the products 0, 4, 1. So let me jot those down to remember. 0, 4, 1. So I've got those as the coefficients. So in this row, I'm going to get 0 on the M, and notice that's missing. I get 4 times the second variable, which is h, and that's what you see here in the handout. There's a 4 there. And then the 1 is for this symbol sigma squared that appears there. So those 3 products give me the second row of this expected mean square column. And then there's only one case left, third row, and that's usually easy. I wonder if our covering the column method does anything on that column. Let's see, if I cover the third column, the products are 0, 1, 1. Now it doesn't seem to work right because I would like to have 0, 0, 1. Right? So that didn't seem to work right. We got to go back to this stupid line here and say, read it again. Are the entries in the column that contain non-parenthetical subscript letters in this term? Then B, multiply the remaining numbers in each row. Each of these products is the coefficient for its corresponding term in the model. And here's the complication. Provided the subscript on the term is also a subscript on the term whose expected mean square is being determined. Now that's kind of slippery. That's kind of tricky to interpret. But there it is. I'll read it again. It says, do this provided the subscript on the term is also a subscript on the term whose expected mean square is being determined. So when I do this, and I look at my 3 products again, 0, 1, 1, I'll throw this one away because it doesn't satisfy that condition. And so I'm left with just the 1 on the bottom, and that's what you see here as the third expected mean square here. So this is a short little exercise because there's only 3 rows here, and you see that the algorithm of following these steps can be carried through to figure out the expected mean square column. So these just don't automatically appear from somewhere. They're the result of following this algorithm. And actually the third page here is the second example of this handout, which was more complex. And so when we look at the model that this data set has, there's more terms in the model to deal with here. And so we have to start the algorithm by listing the terms in the model down here. That's our first step. You fill in this stuff along the top, which is usually pretty easy to do. Label the subscripts and then whether it's fixed or random and how many. That's usually pretty easy to do there. And the trick starts to come in filling out the entries down here. Now I'm not going to do this one in class because this takes a while to go through one this long, but I'll just turn it on your shoulders to say, check this one out. It's a little longer, but it's still a good exercise to check that algorithm to see that you can obtain this column of expected mean squares in this example. Okay, so give that a whirl, see what happens to you. This is kind of a nice old classical statistical idea, a split plot experiment. And the picture here describes pretty well what's going on with this kind of experiment. I like to look at this kind of situation as an agricultural experiment. So I like to say I've got factor A that I want to study. Maybe that's the type of fertilizer that I'm going to use on the crop. And I've got factor B, which could be the planting depth of the seed, for example. And I've got several different planting depths for the seed there. And then factor C, the third factor, is farm. So the picture here says C is 1, that's farm 1. So what you see here on farm 1 is we're going to, at that particular farm, identify a plot of land, a second plot of land, and a third plot of land, like that. And I don't really care how big those are. Those are fairly large plots of land. They're maybe several acres in size, for example. So we identify those, and then basically what you see here at this farm is that I'm going to assign the 3 levels of factor A on these 3 plots of land. But I do that at random. So A equals 3 at random went to this one. A equals 2 at random went to this one. A equals 1 at random went to this one. So I assign the levels of factor A to the 3 plots of land. Okay. Now I go to another farm and do the same thing. So down here you see C is 2 for the second farm. I have a plot of land there, fairly large one, plot of land here, and finally a third plot of land identified here. And I assign the 3 levels of factor A to those 3 plots, again at random. So the randomization apparently said A equals 1 goes here, A equals 3 goes there, A equals 2 goes there. But the assignment of A to these plots of land is done at random separately at each farm. Now these big plots of land are called, where should I write it? Maybe I can squeeze it in here. Are called whole plots. Because then the experiment continues. I've got to get factor B in the experiment somehow or other. So what I basically do is to say, for this plot of land, I'm going to, since I have 4 levels of factor B, I'm going to divide it up into 4 smaller plots of land. And I'm going to assign the values for factor B to those 4 portions. Then I'm going to move over to the next whole plot and do the same thing. I'm going to divide it up, identify, or fence out, whatever I'm doing, 4 portions over here, and assign the 4 levels of factor B, again at random, so it's not always in the same order. Again, assign those B's at random to those 4 plots. Those are referred to as subplots. So in this experiment, we have the whole plots, which are the big pieces of land. And then we have the subplots, which are the smaller portions of land. And then this continues for the other cases as well. So carrying out the assignment of factor A and factor B to the land in this fashion is called a split plot experiment. And you kind of sense the meaning of the name because we have plots, which are the main big pieces of land. And then those plots are split into smaller pieces, as you see in here, and in each place as well, to get the subplots. So we have whole plots, or plots, and then we have subplots, the smaller pieces. And so this is the way the experiment is carried out. Now, if you look at this in the agricultural situation, you can see how this is practical and efficient. If the farmer has to spread a type of fertilizer on the land, he's got to hook up his machinery behind the tractor, and he's got to cover all this with the setting that he has. Then he's got to stop the tractor, reset the machine, change the type of fertilizer, whatever it is in the machine, and he comes over here and he does this big plot of land. And he stops the tractor and he resets the stuff, and then he starts over again and does this one over here. Now, the idea is that for the farmer to be efficient, it's easy for him or her to do a big piece of land all at once. If we had to carry out this experiment in a crossed way, where now the plots of land might be these pieces here. So I got 4, 4, 4, 4, 4, and 4. So let's see, that's 4, that's 24. Well, if I had to do this experiment where I was going to cross A and B, I would say I've got this layout for my land. So those are my plots of land. 4A, 12, 12 boards, 24 in all. There's 24 plots of land. And what I'm going to do is to assign factor A, which has 3 levels, to those 24 plots. So I'm going to assign factor A at the 3 levels and at random to those 24 plots. So you can envision that being done. Now I'm going to turn to assign factor B, maybe the planting depth that was, and I'm going to apply B to those 24 plots of land as well. So in other words, what I'm doing is doing a crossed experiment on the 2 factors A and B. Now, if a statistician was going to tell the farmer, do this to collect your data so I can analyze it properly, the farmer would throw him out. He would say, get out of here, I can't do this because this is too time consuming. I've got to hook up my tractor and go to whatever the assignment is here and lay in the fertilizer in that small pot of land. And then I got to shut my tractor down, change the settings on it, and come here to the next level of factor A, and do that. Shut my tractor down, change the settings on it, come here and do the next level of factor A, and etc. Do it there. So there's a lot of monkeying around for the farmer to do to carry out the experiment this way. And he or she isn't going to want to do it this way. It's just too time consuming and really wasteful of effort. So, and then of course this could be repeated for factor B on each of these 24 smaller blocks of land. So that's the way the experiment might be conducted if we wanted to set up the data so that factor A and B would be crossed. So instead of doing it this way, somebody way back when said, hey, couldn't we do this in some other fashion? And that gave rise to this split plot design type of idea that you saw me writing here. So it's easier to plant or treat land in bigger plots than in smaller plots. And so that was the historical root behind the split plot kind of experiment. And then people in other fields started to notice this idea, and they said, hey, this would work for me as well. I'm not planting crops, I'm studying reading ability of children, for example. I could do something like this as well. So whatever, the idea spread. And so you see here, we have a model equation. So we put in the model equation some familiar things. Yijk. I is for the A level, J is for the B level, and K is for the for the C level. So we have an A effect. I guess in the way this is written, gamma K is the block effect, so that's the C. So that's for factor C. Then I have an AC interaction term. Because if you just let your eyes see kind of standing back, the big picture, factor C and on top factor A, you see that for C versus A, I have 1, 2, 3, 4, 5, 6 cells giving me such information. So factor A and C are just sort of naturally crossed in this layout. And so I have this interaction, AC interaction term in the model. Then we go on and say, well, there'll be some effect on the response due to the B factor. So let's throw in a beta J for the effect of factor B. And now, here's a tricky thing. Let's throw in here an interaction between A and B, an alpha beta ij. And then there's our model. Now, all the terms in the model are fairly explanatory, except for this one. Why do we have that one in there? It might be a question you would have. I have a question about that as well. I'm going to leave it in there. And I just noted down here that different books, different sources, write different models for this split plot experiment. So here's a comment that says, Kuttner omits the block effect gamma K. Well, I don't know why you would need to do that or want to do that. But anyway, our textbook omits the gamma K from the model. Another popular textbook on design and experiment adds another term in this model, a term for the BC interaction. And I don't have that in the model here as well. So this is just a little, perhaps warning, I guess, to say, well, not everybody writes down the model the same for a split plot experiment. You can look up one book's analysis of some split plot data and find something different from another book's analysis of the split plot data. And hopefully the difference isn't enough to cause a different conclusion to come out, but it very well could. So then when we turn the page here to continue on with the story, it basically says, and I'm kind of skipping this, it basically says means are calculated in the usual way, sums of squares are calculated in the usual way, and so there's nothing needed to write down the formulas for those things here, do the usual calculations. So I turn to this example from Kuhl's book. Now in this example, let me see if I can remember what was going on in this example again. A was an amount of nitrogen. B was years, 1, 2, 3. C was blocks, which is probably like farm, 1, 2, 1, 2. And Y is chlorophyll, measured on some sort of plant that was grown. Now, if I try to look at this example and then compare it to what we had on the previous page, block or farm over here on the left is good. C equal 1, C equal 2. What else do we have in this example? We have A is the amount of nitrogen applied. So there's A, that would be there. And then B is years. That doesn't, to me, seem to fit my agricultural appearance here very well, does it? In year 1, I'm going to do B equals 1. So something there. And then the plant is grown, and we take some measurements from it. Then the second year comes around, so we waited a whole year, and we plant different spots for in this subplot business here. But this doesn't fit very well. I would think that maybe this would work better if I would switch A and B in this example, and let A be the year, and B here in this picture be the other variable, the amount of nitrogen. So, for example, in year 1, I might be here and here. And then in subplots, apply the different levels of nitrogen. That fits. And that goes on for year 1. And for year 2, I come over here and here, and in the subplots, apply the nitrogen as appropriate there. And finally, in the third year, I'm here and here, and repeat again. So I think the example fits this picture a little better if I would switch the variables A and B to be different. In other words, if I would say, let's let years be A, let's let nitrogen be B, and let's leave blocks to be the farms as indicated. So I think the picture fits this example a little better with that modification. But anyway, what did I do? So here's the data, and you can see it's a standard data set. The data is arranged in columns by the values for A, for B, C, and then the response Y. So there's the data. And then in Minitab, I can do this with the menu, or I can do this by typing the line. I think I did this with the menu. But anyway, let's just take a look at what was produced. We have C, which is the farm, the block effect, as it's called. We have A, and we have AC, interaction. Then we have B, and then we have AB. So those 5 pieces that I have there in that Minitab would correspond to the 5 pieces in this general model right here. So there they are. I think the order is a little different here versus what I used in Minitab, but that doesn't matter. So anyway, notice I'm just using the simple GLM command. So nothing fancy is needed on that regard. And so C is random. That would be the blocks of the farm. And the others must be fixed since I didn't say they were random. And so we ask for expected mean squares. So C has values 1 and 2, A has values 1 through 4, B has values 1 through 3. We get this ANOVA table. Now in this ANOVA table, one thing that's kind of crucial is the order in which the terms are laid out of these rows. the way things are laid out here and the way they describe it is to say, well, let's see, where should I write this in? Above the line, notice I wrote that line in. We have whole plot information. And then below the line, dealing with factor B and AB interaction, this is the smaller, or the so-called split plot information. So these are separated out. Usually they're separated out by maybe a space. I drew a line here on the handout to make that division. But anyway, this is what's going on. So A and C are for the whole plot information, and then B, the split plot information in the lower part. So degrees of freedom are figured out in the usual way. There's no surprises here. Sums of squares are calculated with the usual formulas. Mean squares, F statistics are here. So what are we using for the F? Well, we need to know what is the expected mean square designation to figure out these F tests. So let's jump ahead to the next page where we have told us what that was. It appears right in there. So the expected value of mean square AB is 6, that's the error, plus expected value of B is 6 plus a term involving B and AB, which is okay. And then for CA, 6 plus 3 times 3. Then for A, 6 plus 3 times 3 plus an A piece. And finally for C, 6 plus 3 times 3 plus a C term. Well, so what this is telling us, if we start on the bottom and work up, it's saying that if we want to test B or the AB interaction, use the error mean square for the denominator. So let's just look at those last 3 lines, and then we can check over here. Hopefully that's what it's done. So we have these bottom 3 lines. Here's our adjusted mean squares is fine. If we use this error mean square as the denominator, if I divide it into the top one, that's about 2, a little less. I divide it by 0.2, I'm going to get something about 9-ish, that's about right. And if I take the AB line, 0.69, I divide that by 0.2, I get something around 3. So that's right as well. So notice anyway that we have used the error as a denominator for these 2 F tests. It tells us that the p-value for B is very small, and B is significant. The p-value for AB is small, but not under 0.5, so I guess we would accept H there. So anyway, in our usual way, make the conclusions about the hypothesis on B and AB. Now we move up to the top, the whole plot type. We need the spot pulled back here. And so if we want to test about CA, we're looking at these right here. And so the proper denominator for the CA interaction would be the error. Okay. The proper denominator for testing either C or A is the CA interaction. So there's a change. The CA interaction is the denominator for the top 2 F tests. So we see that from the expected mean square information. And here, we should basically see that the CA interaction test has a mean square of 0.4. If I divide it by mean square error, which is 0.2, the ratio is about 2. So that's in the right ballpark, 1.95. Now if I want to do the other F test, the proper denominator is going to be the CA interaction 0.4. So the top one, 0.5 divided by the 0.4 1.2, that's about right, and so that's the F. And then the next one, 12 divided by 0.4 is, well, 29 is in the ballpark, so there's a big F there. And so when we look at the p-values, we see not significant, significant, not significant. So in our usual quick way, simply looking at the p-values, we can make the conclusions about which factors and which effects are significant or not significant in our model. So in this particular data set, it looks like we're finding that A is significant and B is significant, and that's it. Yes?
My question relies on why is C random and A is fixed in this case? Because to me, if C is the farm, you don't have like multiple farms. You only have a certain number of farms, like one, or maybe you have two.
Okay, I see what you're saying. You're taking yourself from the point of view of the farmer. The farmer has one farm, two farms.
Right.
I'm taking it from the point of view of the researcher. The researcher can say, I can go out and solicit farms from the whole county.
Okay.
So I've got a whole population of farms, and I'm going to select 2 of them for this experiment.
Okay. So you're saying in general about all the farms?
So this is a conclusion in general about all the farms.
And what about the land then, the fixed A factor?
Well, A is probably tied by the science. What are appropriate levels for nitrogen to use on this crop? It's not a random choice.
Okay. Yeah, that makes sense.
Experimenter would have
Just wanted to make sure.
some preset ideas about the levels for A that he wanted to test about. Sometimes this business of whether a factor is fixed or random is kind of slippery. Like 2 different people might interpret things differently when they look at the situation. So it's not so automatic and clear cut in every example that I can think of. Okay, so there's the ANOVA table, the F-tests, the expected mean square columns that we use, and it's telling us here again, sort of repeating the information, what denominators it is using, and so there we have it. Now, what I did next in Minitab was to say, and here's my little note, let's add one more term to the model, because what terms are in the model is some disagreement across different books. So what I did, as you see here, and compare this to the previous page, C and A we had before, AC we had before, B and AB we had before, and what I've done here, yes, I've added BC. Now, let me try to remember. This model here seems to me to be not this one. There's A, C, AC, B, AB, and it stops. So what I've done is to add another term to this model involving another interaction. And here you see it at the end, the B times C. So I'm just trying to say, what would happen if we had a different model? Analyze the same data, what happens? So here's the output, here's the ANOVA table, and the next page would be the expected mean squares. And well, this is a little hard to compare because you have to look across 2 pages. But anyway, if you look at the expected mean squares, notice that the denominators here are going to be different than what we had looked at before. So now those F-tests are all going to change around, having different denominators. So this will take some inspection on your part to look at these numbers and see that they're following the prescription for the expected mean square information, and it does. But anyway, the main point is to notice that we have different F statistics here. Now, I'm not sure whether the conclusions are the same or not. Here we're finding A is significant, AB is significant, and that's it. A and AB. What did we find in the previous one?
A,
A and B. So our conclusion is quite different. The first run, A and B were significant. In the second run, A and the AB interaction are significant. So we're getting a different answer anyway as far as what's significant and what isn't. So what this shows is that the specification of the model can have a difference in the conclusion that you reach. What's the right model to specify? Nobody knows. Right? The model is chosen by the researcher as to what he or she thinks is reasonable for the situation. And there's no automatic answer to that kind of question. So the model is a, what should I call it, personal judgment by the researcher as far as what should be specified. But notice this shows that the conclusion can depend upon one's choice of model. Well, I think that's a good place to stop for today. Let's leave this example 2 for our next class. I mentioned the dreaded word test last class, so I probably should say something about it yet more today. I'm thinking that maybe our second test could be on the 2nd. I've got to look at my calendar and make sure that that fits a little better for me. But why don't you jot that down as our tentative date for test number 2, the 2nd. And you told me that Magdalena's test was on the 11th, so there's quite a span in there, which is probably good. And I'll say more about that second test soon. Or at least you have a heads up to say that that's when it's coming up. Okay? All right, so let me stop there then for today.